All right. We're now in kinematics with graphs. How exciting. The word of the day today, or sorry, the phrase of the day today is digital footprint because when I rewrote this example to be a little bit funny, I didn't think about my digital footprint. Okay, because the internet is forever, right? Um, Okay, let's talk really quickly about kinematics with graphs. Okay, so if you have an x versus t or position versus time graph, you take the slope of the line at any point gives you the velocity. Okay, if you take the slope of a v versus t graph, that gives you acceleration. Okay, if you take the cumulative area under a v versus t graph, so if you take the area under the v versus t graph and with sine considered as well, then it would be the change in position or displacement. Okay, and then about for an acceleration versus time graph, to if you take the area under acceleration versus time graph, that gives you change in velocity. Okay, it doesn't just give you velocity or position; it gives you the change in those. Okay, so there's a difference. Okay, okay. Starting out, let's take a look at this example right here. So Karen, spelt weird, and there's a particular reason for that, rides her electric scooter along a straight road from her apartment to UNT, which is University of North Texas. That's the college I went to. Starting at her apartment at the time t equals 0 seconds, and arriving at UNT at time t equals 100 or 1,200 seconds. Her velocity vt in meters per second is modeled by the graph shown. So here is her velocity versus time as time goes on. Find the acceleration of Karen's electric scooter at time t equals 750. Okay, well, if we're asking for acceleration, we want the slope of a vt graph, right? So that would be acceleration is equal to slope, okay, which is delta v over delta t. Well, if you notice that t equals 75 seconds, okay, or sorry, 750, which is right about right here, okay, you notice that the slope is consistent. So what we can do is if we just find the slope between 800 and 700, I can do, let's see, it should be 10 minus 15, right? Final versus minus initial, 800 minus 700, okay? And you should end up getting negative 0.05 meters per second squared, okay? You should end up getting negative 0.05 meters per second squared for that, okay? Okay. Um, so then in part B, okay, shortly after leaving her apartment, Karen realizes, oh shoot, she left her derivation of the range equation at home, and she needs that to impress her crush John, and so she returns home to get it. So what time does she turn around to go back home? Well, if you notice, okay, you notice that initially your velocity is you notice your velocity is going in the positive direction, but then you start to slow down in the positive direction, and now you turn around. This part right here is where you turn around. Okay. Then you notice that she speeds up in the negative direction and then stops for a second and then goes back in the positive direction. Okay. So you notice that right here is when she goes from the positive direction to the negative direction. Okay. So that means that she turns around at t equals 200 seconds. So at time 200 seconds. Okay. Because the direction of v changes. Okay. The total distance between the apartment and UNT. Okay. Well, to find the total distance between between her apartment and UNT. Okay. To find the total distance. Sorry, I'm trying to get this under my document camera. Okay. To find the total distance, it's the total area. Okay. With sine. Or in other words, the displacement, right? So we would actually have to subtract any negative area from the thing. This should honestly probably say the displacement between Karen's apartment and UNT. So maybe instead of saying distance, we can say displacement, okay? And maybe I'll keep that in mind next year. Okay, the total displacement between Karen's apartment and UNT. So I need to figure out the area under each segment and then add up all those areas with the sign considered, okay? So notice that this is the first part right here. This is a triangle, okay? This is a triangle right here that's going to have an area 1/2 BH. Okay, my B is 200, H is 10. 200 times 10 is 2,000, and then half of that is 1,000. So this is an area of 1,000. Okay. Again, BH. B is 200, H is negative 10. So this is negative 1,000. Okay, and this should make sense, right? Because this is when she goes out and then she's like, oh shoot, I forgot my range equation at home, and then turns around, goes back home. So these two should cancel each other out. That's perfectly fine. Okay. This part right here has an area of 0, right? Because it's flat line. There's no distance between no area between where the function is and the x-axis. This part right here is kind of weird, so I'm going to break it up into a couple of triangles and rectangles. Okay, here's a triangle right here. Here's a rectangle right here. Okay, here's a triangle right here. Okay, here's a big long rectangle, and then here's a triangle right there. Okay, so you see how I've broken this up into like a bunch of little pieces. Okay, for this small triangle on the left side, our B is 100, our height is 15, and then 1/2 that. So I end up getting 750 for that. Okay, this rectangle has a width of 100 and a height of 15. This gives me 1500. Okay, this tiny little triangle has a base of 100 and height of 5. I end up getting 250. Okay. And then this rectangle right here has a width of let's see, it should be 700. Sorry, 700 to 1100. That's 400. Okay, that's a width of 400 and a height of 10, so it should be 4,000. Okay, and then this triangle right here, 1/2 BH, B is 100, H is 10. Okay, and I should end up getting 500. Okay. Okay, so now what I got to do is just add all of them up with sign considered. You'll notice that the only negative area is this negative 1,000. So really, we're not even going to look at these ones right here. We're just going to look at these ones. Okay, 750 plus 1,500 plus 250 plus 4,000 plus 500. Okay, and when you calculate it out, I ended up getting 7,000 meters. Okay, I ended up getting 7,000 meters when you calculate everything out. Okay, part D says determine the total distance between her apartment and UNT. Okay. Oh, sorry. Oh, sorry. D is the total distance Karen rides before she gets to UNT. So how far is she going? That's basically the length of the path. Okay. This is length of path. Length of path taken. Okay, it's not really clear, I guess. Okay. So to do that, you're just gonna add all areas. Add all areas as positive. Okay, so it's going to be the same. She does this whole same distance right here, the 7,000 right here, but she also does 1,000 going there, and then she turns around and does 1,000 coming back. So we now have to take the 7,000 and add 1,000, 1,000 to give us a total of 9,000. Okay, so that's 9,000 meters. Okay. Okay, and then her average speed, okay. So what is her average speed between t equals 500 seconds and 1,200 seconds? Okay. So the way to do this, right, is that the average velocity is simply the net displacement over the time it takes to do it, right? Okay. And so from 500 to 1200, okay, this is, well, we already said that her net displacement when she leaves her apartment the second time is 7,000 meters. So the net displacement is 7,000 meters, okay? The time that it takes for her to do this is the difference between 1,200 and 500, which is 700, okay? And you should end up getting 10, right? Okay. 10 meters per second for her average speed. Okay. There's the graph again. It's repeated for you. Okay. Just so that you can kind of use it to reference, right? Acceleration is a function of time. So I'm going to do my accelerations. I need to take the slope of every segment here. Okay. I need to take the slope of each segment. So I'm going to do the change, the change in y over the change in x. Okay, 10 over 100, that gives me 0.1, okay, for that first segment. Then for this next part right here, the change in y is from 10 to negative 10, so it would be negative 20, okay? Negative 20 over 200, that's also 0.1. This time it's negative, okay? This part right here is going to be 0.1 again, because these triangles are identical to each other, okay? This part right here has a slope of 0. This part right here going up, okay, it has a rise of 15 and a run of 100, so that's 0.15, okay? This has no slope right there. This part right here has a rise of negative 5 and a run of 100, so that would be 0.05. This should be negative as well, okay? This part right here has 0 slope. And then right here, our rise is 10, our run is 100. That gives you negative 0.1. Okay, so I've got all my slopes. So now what I gotta do is just draw the acceleration function, and it should be a series of steps. Okay, so I'm 0.1 for the first 100 seconds, and I jump down to negative 0.1 for the next segment. Okay, and I do that until I hit 300. At 400, so after 300, so between 300 and 400, I hit I hit 0.1, okay, positive 0.1. Okay. Okay. Then this is 0, so I drop down to 0. Okay. 0 until I hit to get to 500. And then from 500 to 600, I'm at 0.15. Okay. Back down to 0 until I get to 700. Now I'm at negative 0.5 until 800. Man, this is a mess. This is a terrible looking graph, right? Okay, and then thankfully I get a little patch of 0 all the way out to 1100. Okay. And then negative 0.1. What a mess of a graph, right? Looks terrible. Okay, and then the areas. So the area we've already figured out. I'm going to break the areas up into smaller segments. So, one for each. So every 100 seconds, right, has a new area. Okay. So let me just dice up the graph into more segments, right? So I'm just following the dotted lines here. Okay. Well, this right here, right? If this is 1,000, each piece is contributing 500 because they're symmetric. Same here. Okay. This is asking, the final part's asking position as a function of time. Okay. So then this has an area of 0. This right here is going to have an area of 750. We solved that earlier. This part up here has an area of 1500. We solved that earlier. We would take the, 250 plus the, I think it was 1000. If memory serves me correctly, it's the 250 plus the 1000 to get 1250. Okay. Each of these segments right here, 100 of the 10. This is 1000. Okay, 1000. 1000, and then this last part right here will be 500. Okay, so we take the area each part. Okay, so our that gives us our change in area, our change in position. Okay, so to figure out what the position graph would look like, okay, at 0, obviously we're at 0. At 100, we're at 500, so it's going to be right about halfway there. I'm just going to plot the points and then figure out how they should look in a second, okay? At 200, we've gone another 500, so we should be at 1,000, okay? At 300, we moved backwards 500. At 400, we've moved backwards another 500, okay? At 500, we haven't moved any, so it's going to be flat, okay? It's going to be the same elevation. 600, we moved up 750, so it's going to be right about there, okay? At 700, we moved up an additional 1,500. Okay, we moved up an additional 1,500, so we should be at 3250, I think, off the top of my head, right? Okay, so at 700, we should be at What was it? We're at 750. We add to that the 1500. Okay. So add to that 1500. Okay, 750 plus the 1500. So that's two. No, sorry, 220. 2250. Okay, 2250, which is about right there. Okay. At 800. So this is. Let me just write this down so I don't forget here. It's 250. Okay, at 800, when we hit 800, we've moved another 1250. Okay, so then that's going to put us at 3500. Okay, at 900, we're going up by 1,000 now. So 900, we go up by 1,000. At 1,000, we go up by 1,000. At 1,100, we go up by another 1,000, and then at 1,200, we go up by 500 to end up at 7,000. Okay. And then to connect the dots here, right? We would connect the dots here, but we are looking for we want to look at the acceleration, right? So from 0 to 100, it should be concave up because it's positive. From 100 to 200, it should be concave down because it's negative. From 200 to 300, still concave down because it's negative. Okay. From 300 to 400, it should be concave up because it's positive now. At least I'm talking about the acceleration being positive, right? 400 to 500, it should be a flat line. 500 to 600 should be concave up because it's positive. Okay. 600 to 700, there's no acceleration, so it should just be a flat, or sorry, not flat, a linear segment. Okay. From 700 to 800, it should be concave down. Okay. From 800 to 900, it should be flat line segment. From 900 to 1000, flatline segment. From 1000 to 1100, flatline segment. And then concave down to finish us out at that. Okay, so that's how that graph looks. It looks really weird, doesn't it? It's a really funky graph. Okay. All right. There's graphs. Okay. There's graphs, and there goes my digital footprint. Okay. Have fun.